I'm going to illustrate now the use of mixture models for classification using the wine dataset. Unlike the previous datasets that we work with, this one is not included in R by default. So the two files that you need, wine training and wine test, are available on the website. Make sure that you download them and that you have them in the right directory for R to read them. And in this case, I made sure that I change the directory where I'm looking at before I start working with this, and that I put my files in there. Okay, so the wine data set is an interesting one. It's a series of measurements for different varieties of wine. They come from 3 different cultivars. And for each particular variety of wine, they did a chemical analysis and measured 13 different variables that have to do with different chemical components present in the wine. So we have a label set where we know which samples from which of the 3 cultivars. And now we want to use the information that we glean out of that to classify, to decide a series of new wines to assign them to the cultivar that we think they come from. We actually do know the truth for the test set, so we will actually first do the prediction, so we'll act as if we don't know what the cultivar of the test set is, and then we will compare the predictions that we're making against the truth as a way to tell how well the algorithm is doing. Okay, so the first thing that we need to do is load our data set. As I said, you need to make sure that the 2 files are in the directory where you're working, so make sure of that. Remember that we called N the sample size of the training set, and M the training size, the size of the test set. So I'm just calling the variables that way. And I'm going to use a mixture of normals, mixture of multivariate normals, by location and scale. So I'm going to use a method that is essentially equivalent to doing a quadratic discriminant analysis. And I want to run the EM algorithm that I discussed on the board, but in a situation in which we assume that we're going to work with semi-supervised learning. In other words, I want to run the EM version of the algorithm in which we're going to use all the observation, both in the training and the test set, to learn the parameters of the classes. So it's going to be an iterative algorithm. So we know in advance that we have 3 classes because we have 3 cultivars. P in this case is going to be 13 because this is there are 13 features that were measured on each wine. So if you come down here, you can see that P is 13. We can try to do a graph of the data. In this case, the graph is not going to be terribly readable because there are so many variables, but it may still provide a little bit of intuition. So the variables that are measured are things like alcohol, the ash, the alkalinity, the level of magnesium, the hue that has to do with how dark the wine is, proline. So you can see here what the variables are that are measured. And even though the graph is not very readable, at least you can see that the classes do not fully overlap. So we do have some hope that we may be able to do classification in the problem. That's pretty much the main thing that you can say out of this graph here. Okay, so as I said before, mixture of models with different components, different variances and different means for each component, each normal component in the mixture. Same type of standard initialization that we have done before. And we're going to do the E and the M step. Here, remember that for the observations in the training set, we know the class. So the values of B are either 0 or 1. And because we do the calculation first in the log scale, then we do either 0 or minus infinity. So 0 corresponds to probability of 1, and minus infinity corresponds to a probability of 0 in the log scale. And then for the observations in the test set, we have just the regular way in which we compute the probability that the observation comes from each class. And once we have done this, then we do as we have always done, subtract maximums and then re-standardize. So this is how the E step gets adapted in the case of semi-supervised classification. And then the structure of the M step is exactly the same structure of the regular EM algorithm. So we compute means and variances for each one of the components as weighted averages of the different quantities. We check convergence in the standard way in which we have been checking convergence. And finally, once everything is done, we will get a classification. So let's run it for this data set. It runs actually quite quickly. We have only 12 iterations and we have converged. Now, what the EM algorithm gave us is just the V values, that is the probability that an observation comes from a given class. Now, we typically are going to want to convert those B's into C's, and as we saw on the board, that is done by just selecting the class that has the highest probability. So if we do that for our training set in this case, and if you look at the indexes here, they run from n+1 to n+m, which means that we're looking at the test set. If we just get what is the maximum, we can see, that the first block of observations is assigned to component 2. Most of this block is assigned to component 2, except for this guy here. And then the remaining block of observations is assigned to component 3. So now, how does that compare with the truth? So we can actually go into wine.test, and the first column of that file contains the true labels. And we can say that it matches actually pretty well. So the ones all match. The twos match except for one guy, the one that we had kind of identified before. And the threes all match together. And we can actually, if you just want to have a summary of how many errors you make, you can do a little comparison like this. And you can find that there is only a single error in the classification that the algorithm does. Now, let's compare that with just using quadratic discriminant analysis and linear discriminant analysis, the way they are implemented in R. So QDA and LDA are the two functions that you will need. They are part of the mass package. So we first feed the QDA model, and then we use that fitted model to predict the classes. And now if we see what the regular QDA does, is it's going to give me this long list of probabilities for the test set. And we can turn those into labels. And in particular, we can see how many errors we're making in the prediction. And you can see that we make a single mistake, which is actually not the same mistake that we had made before. So if we just look at this one here and we compare it against the classification that our algorithm did, and we compare it against the truth, we see that our algorithm makes a mistake in this observation and QDA does not. And instead, the error is somewhere else in the sample. It's basically here. So you can see that QDA classifies this at 2 when the reality is that it's at 3. So our results are not identical to QDA, even though our method is asymptotically going to be equivalent to QDA, but they don't give us exactly the same result, but they give us very similar accuracy. Interestingly, if you run LDA and you try to look at how many errors you have in that case, you will see that LDA in this case has no errors, even though it's a simpler, more restrictive classification procedure. So this can happen. So it's a relatively large sample. So a difference in a single error is not a very large difference. So hopefully this illustrates how classification or how mixture models can be used for classification in a real life setting.